All right, let's explore. Number 10. The Fermi Paradox. In the summer of 1950, physicist Enrico Fermi was eating lunch with colleagues at Los Alamos National Laboratory in New Mexico when he asked a question so deceptively simple it has haunted science ever since. He looked up from his meal and said, "Where is everybody?" 4 words. The most terrifying question in the history of physics. The Milky Way is approximately 13.6 billion years old. It contains somewhere between 100 and 400 billion stars, the majority of which are orbited by planets. Physicists and astronomers had calculated, using reasonable assumptions about the emergence of life, that our galaxy should be home to thousands of communicative civilizations. The math was straightforward. The conclusion seemed inevitable. Here is where it becomes unsettling. Even traveling at a fraction of the speed of light, a civilization could colonize the entire Milky Way within a few million years. A few million years sounds long until you remember the galaxy has had 13.6 billion years to work with. Any civilization even slightly older than ours should have had more than enough time to spread across every star system, including ours. They should be here. They should be everywhere. And yet, after more than 70 years of searching with increasingly powerful equipment, we have heard nothing, detected nothing, found nothing. The silence is not merely strange. It is statistically impossible if life emerges with anything resembling regularity. Scientists have proposed dozens of solutions, from the idea that intelligence is vanishingly rare to the possibility that civilizations reliably destroy themselves before spreading. None of these explanations are fully satisfying. All of them are, in their own way, deeply disturbing. The Fermi paradox is not one mystery. It is the framework inside which every other mystery on this list exists. A silence so loud it demands an explanation, and every explanation we have come up with is worse than the last. Number 9. The WOW signal. On August 15, 1977, astronomer Jerry Eman was reviewing data from Ohio State University's Big Ear radio telescope when he encountered something that stopped him cold. Buried in pages of routine radio frequency printouts was a sequence of characters so anomalous, so perfectly structured, that Eman circled it with a red pen and wrote a single word in the margin: "Wow." The Big Ear telescope could observe any fixed point in the sky for exactly 72 seconds before Earth's rotation carried it past. The signal Eman found had lasted precisely that long, meaning it may have continued far beyond what the telescope could capture. It was broadcasting at 1420.456 megahertz, the frequency of neutral hydrogen, the most abundant element in the universe. For decades, scientists had theorized that any intelligent civilization attempting interstellar communication would use exactly this frequency, because any sufficiently advanced species would know hydrogen and would therefore know where to listen. The signal was approximately 30 times stronger than the surrounding background noise. It appeared to originate from the direction of the constellation Sagittarius, near the star group Chi Sagittarii. It bore every single characteristic that physicists had predicted an alien transmission would carry: narrowband emission, the right frequency, extraordinary intensity, and an apparent origin beyond our solar system. In 2017, astronomer Antonio Paris proposed that 2 passing comets, FP Cygni and 237P Linear, might explain the signal. That hypothesis was largely rejected because comets do not emit powerful narrowband radio waves at the hydrogen frequency. Despite decades of targeted observation using the world's most sensitive equipment, the signal has never been detected again. The SETI Institute, the Very Large Array in New Mexico, and observatories across the globe have all listened. Nothing. Whatever sent that 72-second burst into space has remained completely silent. We received what may have been first contact, and whatever sent it has not tried again. Number 8. The Kardashev scale and the missing giants. In 1964, Soviet astrophysicist Nikolai Kardashev, working at the Soviet Academy of Sciences, published a framework for classifying alien civilizations by a single criterion: energy consumption. His scale was elegant, logical, and, in hindsight, quietly terrifying. Because if his framework was correct, there should be civilizations out there so large and so powerful that we could see them from across the observable universe. And we cannot. Kardashev defined 3 types. A type of civilization harnesses all the energy available on its home planet, roughly 10 to the power of 16 watts. We are currently sitting at approximately 0.73 on that scale, not yet a true Type 1. A Type 2 civilization captures all the energy output of its star, perhaps by constructing a theoretical megastructure called a Dyson sphere, reaching around 10 to the power of 26 watts. A Type 3 civilization commands the entire energy output of its galaxy, approximately 10 to the power of 36 watts. At that level, the waste heat alone would be detectable across billions of light years. Here is the genuinely puzzling part. The Milky Way has existed for 13.6 billion years. A civilization only 1 million years older than ours, a blink in galactic time, should have had more than enough time to reach Type 3 status. In 2015, a team led by astronomer Jason Wright at Penn State University used data from NASA's Wide Field Infrared Survey Explorer telescope to scan approximately 100,000 galaxies for the infrared waste heat signatures that a Type 3 civilization would inevitably produce. They found no confirmed detections. Not one galaxy showed the unmistakable thermal signature of a civilization that had mastered its own star system, let alone its galaxy. 100,000 galaxies. Billions of years of cosmic time. And nothing that could not be explained by ordinary astrophysics. What could possibly stop every advanced civilization in every galaxy we can observe from leaving a single detectable trace? Number 7. The Dark Forest. In 2008, Chinese author and physicist Liu Cixin published a novel containing a theory of cosmic civilization so logically coherent that scientists and philosophers began citing it in academic papers. Not as science fiction, but as a genuine candidate solution to the Fermi paradox. The theory is called the Dark Forest. And once you understand it, the silence of the universe stops feeling like absence. It starts feeling like warning. The theory rests on 2 axioms that are difficult to refute. First, all civilizations require resources to survive. Second, resources in the universe are finite. From these 2 premises, combined with the impossibility of verifying another civilization's intentions across interstellar distances, a brutal logical conclusion follows. The rational strategy for any civilization that detects another is not communication. It is immediate, preemptive annihilation before the detected civilization can respond, grow, or become a threat. Every civilization is a silent hunter, moving through a dark forest, because making noise is potentially an extinction-level error. If the dark forest theory is correct, the Fermi paradox is solved. Civilizations exist in enormous numbers. They are simply silent because broadcasting is suicidal. The universe is not empty. It is armed. Stephen Hawking warned publicly against intentional messaging in 2010 and again at the 2015 launch of Breakthrough Listen, arguing that contact with a more advanced civilization could end badly for the less advanced one. Astronomer David Brin has raised formal objections to MeTi, messaging extraterrestrial intelligence, on similar grounds. The problem is that we have already been broadcasting for decades. The 1974 Arecibo message, the Voyager Golden Record, launched in 1977. Decades of television and radio signals radiating outward from Earth at the speed of light. We did not know the rules of the forest before we started making noise. We spent decades announcing our location into a universe that may reward silence with survival and noise with extinction. Number 6. The simulation paradox. In 2003, Oxford philosopher Nick Bostrom published a paper in the journal Philosophical Quarterly that arrived at a logical proof physicists and mathematicians have been unable to refute for more than 2 decades. Its conclusion, reached through straightforward probability theory, was this: almost certainly, we do not live in base reality. And if we don't, then the question of alien civilization has an answer more disturbing than any telescope has ever suggested. Bostrom's argument is structured as a trilemma. At least one of 3 things must be true. Either virtually all civilizations go extinct before developing the computational power to simulate conscious minds, or virtually no advanced civilization chooses to run such simulations, or we are almost certainly living inside one right now. The mathematics are unforgiving. If even a single civilization in history has run large numbers of ancestor simulations, the number of simulated minds will vastly outnumber real ones, and any given observer is therefore far more likely to be simulated than biological. The physical universe offers peculiar support for this idea. Space and time are not continuous. They are quantized, broken into discrete minimum units, the Planck length at 1.616 times 10 to the power of negative 35 meters, and Planck time at 539 times 10 to the power of negative 44 seconds. This is precisely what you would expect from a computational substrate, a universe rendered only to its minimum necessary resolution. A 2017 paper by Zohar Ringel and Dmitry Kovrizhin, published in Science Advances, demonstrated that certain quantum systems cannot be efficiently simulated by classical computers, which some researchers interpret as a potential boundary condition of whatever system is running our reality. At the 2016 Code Conference, Elon Musk stated that the odds we are not living in a simulation are approximately 1 in billions. More than a few serious physicists have said something similar in academic language. If the universe is a simulation, the question of who built it has a simple answer. The builders are the only intelligence that definitively exists, and every law of physics we have ever discovered is a line of their code. Number 5. The fine-tuning paradox. In the early 1970s, physicists began noticing something that made a significant number of them deeply uncomfortable, something they could measure precisely but could not explain at all. The fundamental constants of the universe, the numbers that govern how matter behaves, how forces interact, how stars form and burn and die, appeared to have been set with extraordinary, almost incomprehensible precision. Change any one of them by even a fractional amount, and the universe produces nothing. No stars, no chemistry, no life. Just an expanding void of elementary particles with nowhere to go. The cosmological constant, which governs the energy density of empty space and controls the rate at which the universe expands, is fine-tuned to approximately 1 part in 10 to the power of 120. If it were even slightly larger, matter would fly apart before it could clump into galaxies. Slightly smaller, and the universe would have collapsed back on itself long before stars had time to form. The strong nuclear force, which holds atomic nuclei together, is accurate to roughly 1 part in 100. A 2% change in either direction would dissolve all nuclei or prevent hydrogen from forming entirely, erasing the most abundant element in existence before the universe was a second old. In 1953, astronomer Fred Hoyle made one of the most remarkable predictions in the history of science. He argued that carbon must have a specific nuclear resonance state at a very particular energy level, because without it, carbon could not form in stellar interiors. And without carbon, life, as we know it, cannot exist. Since life clearly exists, the resonance must be there. Physicists checked. It was there at exactly the right energy. Hoyle, not a man prone to sentimentality, reportedly said afterward that the universe looks like a put-up job. Cosmologists have proposed 2 broad explanations. The anthropic principle, articulated by physicist Brandon Carter in 1973, holds that we can only observe a universe compatible with our existence. So the fine-tuning only seems remarkable from the inside. The multiverse hypothesis, developed by Andre Linde and Alan Guth from inflationary cosmology, proposes that our universe is one of an effectively infinite number, most sterile, and we simply occupy one of the rare habitable ones. Neither explanation fully satisfies. Both raise deeper questions than they answer. Either we won a lottery with odds of 1 in 10 to the power of 120, or someone adjusted the numbers before the game began. Number 4, the Boltzmann brain paradox. In the late 19th century, Austrian physicist Ludwig Boltzmann was working on the statistical mechanics of entropy, the tendency of systems to move toward disorder, when he encountered a mathematical consequence embedded in his own equations that he could not resolve. It was not a minor technical problem. It was a question about whether any of the ordered structures we observe around us, including our own minds, have the origin we believe they do. The implications were extraordinary. Boltzmann died in 1906, and the problem he identified has not been solved in the centuries since. The logic works like this. In a universe that is infinite in time, random quantum fluctuations will occasionally, across vast stretches of time, spontaneously assemble any configuration of matter whatsoever. This includes fully formed stars, planets, ecosystems, and, most disturbingly, fully formed human brains, complete with memories, sensory experiences, and the firm belief that they evolved gradually over billions of years. These are called Boltzmann brains, and in an infinite universe, they should be extraordinarily common. Far more common, in fact, than brains that actually evolved through the slow process of biological evolution. Physicists Andreas Albrecht and Lorenzo Sorbo formalized this problem in a 2004 paper, demonstrating that it creates a genuine crisis for certain cosmological models. The universe predicted by dark energy, a de Sitter space expanding forever, would produce Boltzmann brains at a finite, continuous rate indefinitely. Caltech physicist Sean Carroll has argued that any cosmological model which produces more Boltzmann brains than evolved observers is self-defeating, because it predicts that the majority of its own observers are experiencing false memories of a history that never happened. There is no way to prove from the inside that you are not a Boltzmann brain. Every memory you have of every scientific discovery, every piece of evidence you believe supports or contradicts alien life, every observation ever made by every telescope ever built could be a false impression assembled by a quantum accident lasting microseconds. If Boltzmann brains dominate the universe's observer count, the cosmos may be saturated with spontaneous minds, each arising in isolation, each convinced it has a history, none of them able to trust a single thing they have ever perceived. Number 3, the Great Filter. In 1998, economist and theorist Robin Hanson published a paper with a title that sounds almost academic until you absorb what it is actually saying. The Great Filter. Are we almost past it? Hanson's argument was careful, measured, and built from the same premises as the Fermi paradox. But where Fermi asked where the aliens were, Hanson asked something more personal. Something that changes how you think about every fossil ever found, every discovery of water on another world, every hopeful sign that life might exist beyond Earth. The argument is this. The Fermi paradox tells us that the path from dead chemistry to a galaxy-spanning civilization must have at least one extraordinarily difficult step, a filter so brutal that virtually nothing gets through it. That filter must exist, because if it didn't, the galaxy would be visibly populated, and it is not. The crucial question, the one that determines everything, is where that filter sits relative to us. If it lies behind us, if the emergence of eukaryotic cells, or multicellular life, or complex nervous systems, or human-level intelligence was the near impossible step, then we may have already passed through the worst of it. we may be rare survivors of a filter most life never crosses. We may be, in a strange sense, safe. But if the filter lies ahead of us, if some catastrophic barrier awaits every civilization that reaches our level of technological development, then the silence of the universe is not evidence of our rarity. It is a death toll. Candidate filters ahead of us include nuclear warfare, engineered pandemics, artificial intelligence that destroys its creators, self-replicating nanotechnology, catastrophic resource collapse, or contact with a civilization that treats our existence as a threat. Stephen Hawking stated in his 2015 and 2016 BBC Reith lectures that he did not believe the human race would survive the next 1,000 years without spreading into space. Here is the most disturbing implication of the Great Filter, the one that changes what it means to explore the cosmos. Every time we search for life on Mars, on Europa, on Enceladus, we are hoping to find nothing. Because finding microbial life on another world would mean life arises easily and commonly, which pushes the filter ahead of us rather than behind us, which means the worst is still coming. The day we find life on another world may be the day we learn that we are already running out of time. Number 2. The doomsday argument. In 1983, physicist Brandon Carter was working on the mathematics of the anthropic principle when he arrived at a statistical argument so clean, so logically inescapable, and so profoundly unwelcome that philosopher John Leslie spent the better part of his career attempting to find a flaw in it. Leslie eventually published his conclusions in 1996 as The End of the World. He could not find the flaw. The argument, now known as the doomsday argument, states that you can calculate approximately when humanity will go extinct using nothing more than the fact of your own existence and the mathematics of probability. The reasoning begins with a thought experiment. Imagine you are drawing a marble at random from an urn containing either 10 marbles or 1,000 marbles, and you draw marble number 7. That result is far more consistent with an urn of 10 than an urn of 1,000. You are almost certainly near the total rather than near the beginning. Apply this logic to humanity. Approximately 108 billion human beings have ever been born. The current world population sits at roughly 8 billion. If you treat yourself as a randomly selected observer from the full set of all humans who will ever live, the mathematics suggest you are most likely positioned somewhere near the middle of that sequence, not near the beginning of an enormous future population. In 1993, astrophysicist J. Richard Gott published a formalization of this calculation in the journal Nature. His median estimate placed human extinction within roughly 9,120 years, though the full 95% confidence interval extends considerably further. The self-indicating assumption, developed by philosopher Nick Bostrom, challenges the argument by questioning whether you can treat yourself as a randomly selected observer. But Bostrom's counter-argument has not definitively resolved the paradox. It has only clarified exactly what assumptions you must reject to escape the conclusion. Applied to alien civilizations, the argument becomes something stranger still. If the doomsday argument holds universally, then it applies to every intelligent species that has ever existed anywhere in the cosmos. Every civilization, no matter how advanced, no matter how promising, faces the same statistical pressure toward extinction. The Fermi paradox then becomes not a mystery about where civilizations went, but a logical prediction that they could not last long enough to reach us. The mathematics of our own existence may be the most honest account we have of why the universe is quiet, and what that silence is quietly promising us in return. Number 1. The quantum immortality paradox. In 1957, a doctoral student at Princeton University named Hugh Everett III submitted a thesis proposing a solution to one of the most persistent problems in quantum mechanics. His supervisor, physicist John Wheeler, nearly rejected it. The broader physics community received it with indifference or dismissal. Everett eventually left academic physics entirely, his work largely unrecognized in his lifetime. What he had written was, in retrospect, one of the most consequential and most disturbing ideas in the history of science. It is called the many worlds interpretation of quantum mechanics. And buried inside its mathematics is a paradox that does not merely suggest alien civilizations exist. It suggests that the universe's deepest structure makes their survival, in some branches of reality, essentially guaranteed. Everett's core claim was this: when a quantum event occurs, the universe does not randomly select one outcome and discard the others. Every possible outcome happens, each in its own branching reality, each equally real. The wave function does not collapse. It divides. In 1987, computer scientist Hans Moravec extended this framework to conscious observers, and in 1998, physicist Max Tegmark at MIT formalized the implication now known as quantum immortality. Because an observer always finds themselves in the branch where they survive any given event, subjective experience is necessarily continuous across branches. You cannot experience the branch where you die. You always, from the inside, survive. Applied to civilizations, the implications are extraordinary and deeply strange. Any civilization that could survive a given extinction event, whether through technological achievement, sheer chance, or some combination of both, does survive in at least one branching reality. Nuclear war, asteroid impact, artificial intelligence, climate collapse, contact with a hostile species. In the many worlds framework, every catastrophe that admits any possibility of survival produces at least one branch where survival occurs. Advanced civilizations are not filtered into extinction. They are filtered into the branches where they overcame every obstacle, accumulated knowledge across millions of years, and became something we do not have adequate language to describe. This is where the paradox becomes genuinely horrifying. Many worlds quantum mechanics, taken seriously by a significant fraction of the world's theoretical physicists, does not solve the Fermi paradox. It makes it catastrophically worse. If every civilization that could survive does survive in some branch, then the branches accessible to us, the branches where both humanity and ancient alien civilizations exist as contemporaries, should be saturated with survivors, millions of years old, unimaginably capable. And we are in a branch that appears, by every instrument we have ever built and every signal we have ever listened for, to be completely empty of them. The most disturbing possibility raised by modern physics is not that we are alone in the universe. It is that we are alone in this branch of it, separated from an infinite population of surviving civilizations by the very mechanics of quantum reality itself, forever unable to reach them, forever unable to hear them, surrounded on all sides by an absolute silence that the equations say should not, by any right, exist. If you want to see more videos like this, click the video on screen now and make sure to subscribe.